This lecture is part of a series of lectures on rings and modules and will be about projective modules. So I'll start by motivating these with an example. Suppose you've got an exact sequence of modules, A goes to B, goes to C, goes to 0. And suppose M is another module over some ring. Then we can look at homomorphisms of these modules to M. So we get hom A to M, hom B to M, hom C to M, and hom from 0 to M, which is of course just 0. And I want to make these into an exact sequence. And the only tricky point is the arrows go in the opposite direction to what you might expect. So here the arrows are going rightwards and here they're going leftwards. And the reason for that is you've got a homomorphism from B to M. You can compose it with a morphism from A to B and get a homomorphism from A to M, but you can't sort of go back from this group to this group. So we've got a sort of contravariant functor in some sense. And you can ask, well, why don't we extend this a little bit? Why didn't we have a 0 here? And then you might hope that you're going to get an exact sequence like that. Well, the trouble is that fails. For example, if we take 0 goes to Z, goes to Z, goes to Z over 2Z, goes to 0, where this is multiplication by 2, and we take M to be Z over 2Z, well, the homomorphisms from Z to Z over 2Z are just Z over 2Z, so we get this, and homomorphisms from Z over 2Z to itself are just Z over 2Z again, so we get 0 there. And this is multiplication by 2, and if we try and look at this bit, you see this is not exact, because this map is not onto, it's actually the 0 map. So we can't quite turn exact sequences into exact sequences with this operation. And this is a source of endless complications in algebra. In fact, there's an entire subject called homological algebra, which is more or less entirely about trying to fix this fact that when you take an exact sequence there, you don't get an exact sequence here. So homological algebra explains exactly what the obstruction to this is. Well, there's one case in which we can do this. Suppose that C is free. Suppose C is a free module, then if we look at 0 goes to A, goes to B, goes to C, goes to 0, this sequence splits. We find that B is more or less equal to A plus C. Well, it's not quite equal, it's really equal to the image of A direct sum something. And the point is that if C is free, then we can find a homomorphism going back in that direction, such that if you go from C to B and then back to C, you get the identity map. And this follows easily. Let's take a basis for C consisting of elements C1, C2, and so on. And you can map Ci to something in B with image Ci. And since C is free on these, this defines a map from C to B, and you can easily check that it has the appropriate properties. And if you've got a map going the other way, then B splits. B is equal to the image of A plus the image of C under this map F, say. And if B is equal to a direct sum, then it's very easy to check that the sequence you get here is just exact, because this is just the direct sum of these two groups here. Notice this sequence, there's no map from Z over 2Z back to Z causing this to split. So this property definitely fails for modules in general. It turns out that this property of free modules is, first of all, it's one of the most useful properties of free modules, and secondly, there are quite a lot of modules that aren't free but still have this property. And these are roughly the projective modules. So let's define projective modules. So a projective module is one with the following properties. Suppose you've got a map from B to C that is onto, so this is exact. And suppose we've got a projective module B mapping to C. Then you can lift it to a map to B that factorizes through this. This lift need not be unique, of course. For example, when we were splitting exact sequences, up here we were just taking C to be equal to P and taking this to be the identity map. But it turns out to be much more useful to allow more generally P to have a possibly non-identity map to C. So that's the definition of a projective module. It's one with this useful lifting property. So let's have some examples of projective modules. First of all free modules are projective. This follows from exactly the same argument that I had on the previous sheet. All you do is you take a basis for your projective module and you map the basis of your free projective module to B, and that gives you a factorization of this map like that. There's another very easy way of getting projective modules. If F is free and F equals P is the direct sum of P and Q, then P and Q are projective. This is very easy. In fact, it's so easy I'm just going to leave it as another exercise. In fact, F doesn't need to be free. F can be a projective module, and any direct summand of a projective module you can then easily check is also projective. I should put in a warning here. Submodules of free, or for that matter projective modules, need not be projective. And there are lots of examples of this. For example, you can just take the module kxy over the ring xy, and then a submodule that's not projective is the ideal generated by x and y. But anyway, so in order for a submodule of a free module to be free, in order for a submodule of a free module to be projective, it needs not just to be a submodule, but it must have a complement. In fact, the converse is also true, because if P is projective, then there is some free module mapping onto P, because for any module we can find a free module on it. And because P is projective, this splits. We can find a map from P going backwards. So F is equal to P, the image of P, plus the kernel of this map G from F to P. So a module is projective if and only if it's a direct summand of a free module. And this is a really useful way of constructing projective modules. In fact, most of the examples we will give now use this property of projective modules. So now we should find an example of a projective module that's not free, just to show we really have got something more general. Well, there's one really simple example. Let's just take the ring to be z modulo 6z. Now we know z over 6z splits as the direct sum of z modulo 3z plus z modulo 2z by the Chinese remainder theorem. And we can see that this is a free module of rank 1. So z modulo 3z is therefore projective because it's a direct summand of a free module, but it's obviously not free itself, because any free module, the number of elements must be a power of 6, and that obviously fails for this. Well, that example is a little bit not entirely convincing. The trouble is this ring has 0 divisors. And if a ring splits as a direct sum like this, then it inevitably has zero divisors. So what we would really like are some examples that don't have zero divisors. And there's one example that everybody has come across, although they may not have actually realized it was a projective module. And this example is the Moebius band. So the Moebius band is this one-sided surface. You probably did this in high school math classes or something. You take a strip of paper and you join its ends together so you get a sort of twist in it and you get a one-sided surface. Well, you may think this one-sided surface doesn't look very much like a module. So how do we make it into a module over a ring? Well, what we do is we take the circle S1 and we project the Moebius band onto this circle. And we project it in such a way that the fibre at each point, in other words, if you take a point and you take its inverse image, the inverse image is going to be a line. And we're going to say the fibre of each point. Well, you might say the fibre of each point is going to be the unit interval. Well, that would be a closed Moebius band. Well, we're going to take an open Moebius band where the fibre is an open unit interval, and we're going to say, well, we can identify the open unit interval with the copy of the real numbers as a topological space. So I'm going to say the fibre of each point is a copy of the reals. And now I'm going to take the ring R to be continuous functions on S1. That's continuous real valued functions. And the module M is going to be sections of the Moebius band. What I mean, this is going to be functions from S1 to the Moebius band that map each point to something in the Moebius band above that point. So for this point here, you're going to take some function there, and more generally, you're going to have a sort of function that looks a bit like that. And you can see that M is a module over R by pointwise multiplication. You see, we said we're going to identify the fibre of each point with a copy of the real numbers, so it's a one-dimensional vector space over the reals in some sense, and then you can just multiply a point in this one-dimensional vector space by a real number and get another point. Notice, by the way, there's no way to globally choose the isomorphism of a fibre with the reals in a coherent way. You can kind of do it locally, but as you go around the Moebius band, this kind of breaks down. So you can also write down this module structure more explicitly. So we can take R to be functions on a circle. Well, functions on a circle, we can just think of this as being periodic functions. So f of t is equal to f of t plus 2 pi. Let's just measure the circle in radians or something. And then the Moebius band, or rather its module, is going to be functions with f of t equals minus f of t plus 2 pi. And if you think about it a bit, that's sort of the same as the thing I defined earlier. You can think of when you go once round the circle, you're kind of changing the orientation of this vector space, which corresponds to changing the sign of this function. And then you can see that M is not a free one-dimensional module over R because you can't take a non-zero section of it. If you try and take a function of M that's non-zero, a map to M that is non-zero everywhere, you can't do it because of this sign change. If a function has this property here, it can't be non-zero everywhere. Easy exercise in calculus. However, M plus M is equal to R plus R. Now this is free, and M is now a direct summand of a free module, so this implies M is projective. And I'm going to give two ways of seeing this, an algebraic way and a geometric way. So the algebraic way says that if you want to map r plus r to m plus m, you take fg in either r plus r or m plus m. It doesn't actually really matter. And then you map this to cosine of t over 2 f of t plus sine t over 2 g of t. And then the other one is minus sine of t over 2 f of t plus cosine of t over 2 g of t. And you can see that this transformation takes periodic functions into antiperiodic functions and vice versa. So this takes m plus m to r plus r, and in fact it takes r plus r back to m plus m. So these two modules are in fact isomorphic. So that's an algebraic way of seeing this. There's also a geometric way of seeing this. What you do is you think of the circle S1 and you look at the Moebius band over it. And what you do is you think of this Moebius band as being embedded in R3, and you take its 0 section. Guess I should have used a colour that's a bit different from black. And what you do is you sort of take the normal bundle to this 0 section in R3. So at each point you take a copy of the reals that is orthogonal to the Moebius band. And what you can see, if you've got a good imagination and if you draw a better picture than this, is that these normal bundles form another copy of the Moebius band. And the sum of these two Moebius bands, by which I mean at each point you take the direct sum of the two copies of R corresponding to the Moebius band, is just the normal bundle of the S1 lying in the centre of your first Moebius band. And the normal bundle of S1, it's not difficult to see, is just a trivial bundle, so it corresponds to the sum of R plus R. So there's either a geometric or an algebraic way of seeing this equivalence. Now let's see an example. In fact, I mentioned this in a previous lecture. Here I'm going to take the ring R to be Z with root minus 5 attached. So you remember this was the standard example of a ring without unique factorization. We had 2 times 3 equals 1 plus root minus 5 times 1 minus root minus 5. And we remember saying that a consequence of this is that it has a non-principal ideal. And the non-principal ideal is just a module, which can be the ideal generated by 2 and root minus 5. And what we're going to do is to show that this is projective. We know it's not free because it's not a principal ideal, as we saw in an earlier lecture. So all we want to do is to show it's projective, and we're going to show it's projective by showing that m plus m is isomorphic to r plus r. So just as before, it's going to be a direct summand of a free module of rank 2. And there are several ways to see this. One way is to just take a map from r plus r to m, and we can define a map which takes a, b to, well, m is generated by 2 and root minus 5, so we will have a surjective map if we map this to 2a plus root minus 5b. So there we've got a map from this rank 2 free module onto M, and now we notice that it actually splits because there's a map going the other way, which takes a map an element x in M to minus x times 1 minus root 5 over 2 times x. So this is in R plus R. And you may be a bit suspicious of this because here we're dividing by 2, but this doesn't actually matter because we notice that if x equals 2, then 1 minus root minus 5 over 2 x is equal to 1 minus root minus 5, which is still in R, and if x is equal to 1 plus root minus 5, then 1 minus root minus 5 over 2x is equal to 6 over 2, which is equal to 3, which is still in R. So this 2 doesn't actually matter. As long as x is in the ideal M, then this is actually still in R. So this is actually a well-defined map. And you can, since we've got a map back the other way, this means that R plus R is equal to the image of M plus whatever the kernel of this map is. And you can check the kernel of this map is just the set of all vectors root minus 5 minus 1 over 2y times y for y in M. And as before, this is always actually in R. So we have a completely explicit decomposition of R plus R as a sum of 2 copies of M, which shows that M is projective. By the way, you notice there's a very close analogy between this and the Moebius band. In both cases, we have a module such that M plus M is isomorphic to R plus R. And this is not a coincidence, that they're both actually special cases of line bundles. So what's a line bundle? Well, a line bundle is very roughly a map from one space to another, such that the fibre at each point is a one-dimensional vector space. And the Moebius band is obviously a line bundle over the circle. Well, how on earth is this ideal here a line bundle over something? Well, in algebraic geometry, we look at the spectrum of a ring R. So you remember this is the set of prime ideals with some funny topology. And if you think of the spectrum of this ring R as being some funny topological space, then it turns out there's a sort of line bundle over it. In fact, in algebraic geometry, any module over z root minus 5 can be used to provide something called a sheaf over this topological space spec of z root minus 5. Okay, explaining this in detail takes about half a semester of algebraic geometry, so I'm going to kind of skip the details of this. But if you start with this module 2, 1 plus root minus 5, then this actually gives you a sheaf that is actually more or less a line bundle. In fact, geometrically, it kind of looks a bit like the Moebius band. So this gives a sort of geometric way of thinking of projective modules. So projective modules sort of look geometrically a bit like vector bundles. So a vector bundle is kind of like a line bundle, except that instead of the fibre being a one-dimensional vector space, it can be an n-dimensional vector space. So we'll see a few examples of that in a moment. So anyway, the conclusion of these two examples is that Moebius bands that you find in algebraic topology and non-principal ideals that you find in algebraic number theory are actually really sort of the same thing. They're both sort of slightly twisted versions of free modules in some sense. So for the next example, I'll first of all start with some motivation. So we said that if P is projective, then we can find another projective module Q such that Q is free. So here P is projective. And we can ask, can we choose Q to be free? And the answer is yes. And the proof of this is a very neat proof known as the Eilenberg swindle for some reason. So what we do is we take the module P plus Q, which is free, and then we add it to P, and we add it to Q, and then we add P, and then we add Q, and we keep going. And this is a free module. And it's easy to see that this is a free module because this bit is free, and this bit is free, and this bit is free, and so on. So we've just added up a lot of free modules. On the other hand, we can also write it as p plus q plus p plus q plus and so on. And now let's look what we've got here. Well, here we've got p, and here we've got q plus p, which is free, and here we've got q plus p, which is free, and so on. So this is also a free module. So in fact, we've found a free module such that p plus f is isomorphic to f. The next question is, the only problem with this module f is that f is sort of definitely infinite dimensional, infinite rank of something. So we can now ask, can we find q free with q finite dimensional? Well, I haven't actually defined what finite dimensional means for projective modules, but it's mostly obvious what this means in practice, so we won't worry about that. So I want q to be sort of not infinite dimensional, such that p plus q is free. And the answer is sometimes. So I'm going to give two examples, one where you can do this and one where you can't do this. So the first example is where you can't do this. Let's just take M to be the Moebius band example. And this means that every time you go round the circle once, you kind of insert a factor of -1 somehow. You sort of change the orientation of the fibre or whatever. And the same thing is going to happen even if you add a finite number of free modules to M. You're still going to end up with this minus sign whenever you go once round. So M plus R to the n is never going to be R to the n plus 1. Notice that if you added an infinite number of copies, this argument wouldn't work anymore because you can't define the determinant of an infinite matrix. This proof is sort of assuming we can define the sign of the determinant of a matrix, which works provided n is finite, but not if n is infinite. So that's an example where you can't. And a non-trivial example where you can, let's take M to be the tangent space of S2, or rather the module of this. So S2 is going to be a two-dimensional sphere, and at each point we can draw a little two-dimensional tangent space. And our ring R is going to be continuous functions on the sphere S2. And our module M is going to be sections of the tangent bundle. So what this is at each point you're just choosing a little vector in the tangent space, and this is just going to be tangent vector fields on S2. And this is a module over continuous functions because the module structure is, as before, just given by pointwise multiplication. So we've got a module and some sort of so we've got a ring of continuous functions and a nice module over it. And what we want to do is to now show two things. First of all, we want to show that M is projective. And we're not only going to show that M is projective, but we want to show that M plus R is isomorphic to R plus R plus R. And the other thing we want to show is that M is not free. And this may be a little bit surprising because if M plus R is R plus R plus R, you'd have thought you would cancel out the two R's and find M is R plus R. But this is an example where this cancellation doesn't actually work. You can't cancel modules in general. So let's first of all show that M is plus R is isomorphic to R plus R plus r. Well, this follows easily because this is going to be, comes from the tangent bundle of S2, and this r is just the normal bundle. So the normal bundle of S2 just means at each point you take the one-dimensional vector space of things that are sort of orthogonal to the sphere of that point. So it's the orthogonal complement of the tangent bundle. And then you can check the normal bundle is isomorphic to a one-dimensional trivial bundle, because you can take a non-zero section of the normal bundle just by, say, taking the distance from the sphere in an outward direction or something like that. And the sum of the normal bundle and the tangent bundle at each point can be identified, the sum of the normal space and the tangent space at each point. So the tangent space at x plus the normal space at x is canonically isomorphic to R3. And it's important that it should be canonically isomorphic. The tangent space at each point is isomorphic to R2, but there's no sort of canonical way to do that. You can't do this, make this isomorphism global, as we'll see in a moment. So anyway, since it's canonically isomorphic, this means the tangent bundle plus the normal bundle is isomorphic to the sum of 3 copies of the trivial bundle, which is essentially giving us this relation here. Notice that this works for any smooth, compact, I'm not sure you really need compact, hypersurface in any n-dimensional space. So this is a sort of very general property of normal bundles and tangent bundles. To finish off, the one thing we need to show is that M is not R plus R. And this follows from the hairy sphere theorem, which says you cannot comb a hairy sphere. In other words, if you're trying to comb a sphere by choosing a nice tangent bundle at each point, there must be some point at which you have to choose the 0 tangent vector. You can't comb it nicely everywhere. And this implies that M is not R plus R, because if M were R plus R, then you could comb the hairy sphere by choosing a non-zero a sort of generator of this R, and this would give you a non-zero tangent vector field at each point. You notice that this applies to any manifold, any smooth manifold with non-zero Euler characteristic. I should say any compact manifold. So there's a theorem in topology that says if a compact smooth manifold has non-zero Euler characteristic, then any tangent vector field on it must have a 0 somewhere. So the sphere has Euler characteristic 2, which is non-zero. If you look at something like a torus, which is Euler characteristic 0, then you can indeed comb it, because, for instance, we could just comb it nicely by going round in that direction like this. So these examples of projector modules that are not free are very common. We can take sort of any smooth manifold of codimension 1 in Rn with non-zero Euler characteristic, and we will get another example like this. So we're just doing S2 as being the simplest case of this. Okay, I think that's enough about projective modules.